No. It wasn't so bad, though. I didn't actually say the swear word. I just said the letter associated with it. So, like, it's not so bad. All right, so dissociations. Oh, I need to make sure that the sound is recording also. And why is it making all this stupid noise? There we go. Is my sound recording? Yes, my sound is recording. Yay! We are on page 96. When you are looking at a diprotic or a triprotic acid, only the first dissociation is important in Ka calculations. Okay? Only the first dissociations is important, and that's because the Ka value of the first dissociation is much bigger than the Ka value of the second dissociation. So you get lots and lots of hydrogen from the first one because it ionizes a lot, and then the second one produces such a small amount in comparison that you can just ignore it. Yeah. So diprotic acids usually they do undergo two dissociations. It's not like the second one doesn't happen, but only the first one produces significant quantities of hydrogen, H+. The second dissociation, so the first produces significant H+. But the second, some H+, but only a very small amount, so we can just ignore it. So if we are doing something like, what is the H+ concentration in a 0.2 molar solution of carbonic acid? You write the formula of carbonic acid and you decide if it is strong or is it weak. Is it strong or is it weak? Carbonic acid. Go look on your table if you don't know. H2CO3 is weak, and if it is weak, what tools do we use? Rice and Ka. All right, excellent. So if it were strong, you would just write the dissociation and use the stoichiometry, okay? I think you guys are pretty good at that at this point. So since it is weak, we start with the Rice table, but which one do we write? Do we write H2CO3 goes to a single H plus HCO3 minus, or do we write 2H plus and CO3 2 minus without the H? Which one? The top one. Okay, so you do not take off the second H. So remember, only the first dissociation is important in Ka calculations. In diprotic acids, the dissociations take place one at a time. So you will have dissociation number 1 is what we just wrote, right? We have the H2CO3 becoming HCO3. And then secondly, we have our second dissociation number 2, where the HCO3 loses the second hydrogen, and we just have CO3 2 minus. But we just ignore the second one. This applies for all polyprotic acids, at least in chemistry 12, so just do the first dissociation and ignore any others. So for example, what is the hydrogen ion concentration in 0.2 molar carbonic acid, we would do our Rice table. Remember, when you are given a concentration of the acid, is that the initial or the equilibrium concentration of H2CO3?
Initial.
That is the initial. Okay?
Wait, is there something about putting in a flask? No, that was the last unit.
Yeah, and with this one, we are putting it probably in a flask or a beaker.
You just assume that
It's in a container. But the flask isn't as important as when you have gases, because if you have a gas, you need to put it in a flask and put a stopper on it. Right? With this one, the container, yes, you need something to contain the water, but the water keeps because these are all aqueous, they have to stay in the water, right? So the water is almost like the container, yeah? And then you would do what you did yesterday, plus x, minus x, etc., 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 right? And then what would you do after this? You would write your Ka expression. And what does the expression have in it? Does it have numbers in it?
Well, concentration first.
Concentrations first?
Species.
We don't put numbers in first.
No, of course.
We put the species in first, in square brackets. So species first. There we are. Plug in the numbers. There we are. Assume x is insignificant and make sure you point the arrow at it so we know which one we're talking about. Okay, we're not saying this one. This one is not insignificant. That one is perfectly good. Okay. And then you do the algebra. All right. And then you get x, and you say, what was I asked for? I was asked for hydrogen ion concentration. That is x. So that was easy. So that's all we need. What if we were to have done the second dissociation? So we ended up getting 8.6 times 10 to the minus 8. And
that be our initial then?
That is your initial, yes. Yes, because it's the hydrogen, but it's also the HCO3 minus, right? So we can look at it and we can go, okay, I've got HCO3 minus, but my hydrogen is also already at the equilibrium concentration. Don't worry about this. You never have to do this. So if this confuses you, you can just close your eyes and shut your ears for the next couple minutes, okay? And you would still have to shift to the right because the carbonate is still at 0. So you get what you get. You would plug in, you would get your Ka expression, you would plug everything in, and you get a quadratic expression. And I actually did the math with the quadratic formula. And you get, once you churn through all of the math, you get 8.6 times 10 to the minus 8 plus 5.6 times 10 to the minus 11, which is the H plus from the second dissociation. And when you add them, you get 8.6 times 10 to the minus 8. So it was indeed insignificant. So that's just there to say, hey, second one is insignificant. Now, I do have a caveat for you, and it won't matter for this unit, but it will matter for unit 5. When you're doing Ka calculations, only use the first dissociation. But in unit 5, we are going to be reacting a strong base with a weak acid, perhaps. Yes? Now, if I do that, di- and triprotic acids react completely with strong bases. All of their hydrogens react. So you won't just get, this is what you won't get, so don't write this down. Do not write this down. Okay? Do not write this down. I do get people writing this a lot because they're like, only the first hydrogen comes off. But that's when you're looking at that acid in isolation. So let's look at it this way. If I have my H2CO3, one more. If I have my H2CO3 and it goes into solution, how many of these will dissociate? Not very many. One. Do you get very much of the second dissociation? Like with 3 particles, there's not even enough to worry about, yes? But, if you're a strong, I need 3 volunteers, please. Yes, Tree, and you guys, excellent. 2 here, here we go. All right, let's turn this off so it doesn't blind you. All right, and I just want you to stand up here and hold on to these. Okay, 1 there, and 1 there, and face forward, 1 there.
Which forward?
Now, hold it so I can see both the hydrogens. Perfect. Okay. Now, let's say I am a strong base. Yes? What do? I grab hydrogens. So I am 1 molecule of a strong base. La 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 la. Okay? Now, am I the only molecule of strong base, or are there a whole bunch of me? In solution. There's a whole bunch. Yes. La 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 la. So, and every time I go up here, I'm pretending I'm making a molecule of OH, right? So anyway, and I'm gonna speed up the, I'm not gonna speed it up that much, that was hard to get off. I'm gonna speed this up by doing a whole bunch of NaOH molecules, yes? Now, how many H's are left on my CO3s? None. Why? Because there was a strong base who came along and took all of them. So although, if this was just sitting here on its own, here, put those caps back on. If that was just sitting there alone and there was no strong base, okay, I'm gone. Hold up your pen. How many hydrogens have dissociated? Just 1, right? And you're not going to get that second dissociation. But the moment a strong base comes along, all the hydrogens get ripped off. Thank you guys so much. I appreciate it.
I don't get the second part of it.
Okay. All right, we got 1 here. We got 1 here. Put these all back so they don't dry out. So exciting. So it's not like this. No. Oh, thank you so much. It goes Na2CO3 plus H2O. Both the hydrogens will come off. And we would need 2 of these. Yeah? So all the hydrogens react with strong bases. So you end up ripping off all the hydrogens because a strong base is good at grabbing them. So you will have to, when we get to Unit 5, I will remind you of that again, that when it's by itself, only the first dissociation matters because it is dissociating on its own. When it is reacting with a strong base, the whole thing goes to completion because the strong base is busy ripping those hydrogens off of there. Yes? Okay. And that is it for that. So there's nothing really new in this section. You would do diprotic and triprotic exactly the same way as you did the questions yesterday for Ka. All right, next. Weak acids. Do you remember how we found KEQ from data back in the day when we did KEQ? Now we're going to find Ka from data. And if you don't remember, it's okay because we will remind you. All right. If we are given hydrogen ion concentration and we are given the concentration of the acid solution, then we can find the Ka value. Our unknown becomes the Ka rather than the hydrogen ion concentration. So, for example here, these ones are going to be unknown acids, so you can't just go look them up on the table, right? I can't say, what is the Ka of HF? Because you'll just go look it up on the table. So it's here we have an unknown diprotic weak acid is found to have a hydrogen ion concentration of 0.60 molar when we mix 2.50 molar of the acid. Calculate Ka for this acid. So first thing we need to do, write the dissociation. Okay, here we are. And remember, in a diprotic acid, only the first dissociation is important. Is this concentration of the acid is that concentration the initial or is it the equilibrium? It is the initial concentration of the acid. Always initial concentration of the acid when it's given in the question. This solution is found to have a hydrogen ion concentration of 0.060 molar. Is that the initial concentration of hydrogen or the equilibrium concentration?
I think it's still initial only because
What's the initial concentration of hydrogen? Always 0. So the initial concentration of hydrogen is still 0. So what is this, initial or equilibrium? Equilibrium. Because the initial concentration of H plus is always 0, because at the start, none of it has dissociated. So there we go. In this little thing here, the concentration of the acid is always the initial concentration, the hydrogen ion concentration, or you might be given a pH, is always the equilibrium concentration. So when we first, what happened there? When we first placed H2A into solution, none of the acid is undissociated, so the initial concentration is 2.50 molar. And the concentration of H plus is the same as HA minus, which is 0 molar initially. And so our first row of our rice table looks very much like what our first row of the rice table looked like before. Yes? We have our initial concentration, we have 0, and we have 0. Now, we also know now, though, that we have 0.60 molar. Yes? So we filled in this part. The second thing we're going to fill in, so this is number 1, this is number 2, because we are told that that's 0.60. And if we know that hydrogen is 0.06, then we also know that HA is 0.06. Please do not write plus X here. Why not? Because it's a given value. It is not an unknown. X is used for unknowns. We know the value of X, so please fill in that it is plus 0.6. So that's going to be number 2, you know the final, and number 3, you're going to fill in the change. And because those went up by 0.6 and these are all 1 to 1 to 1, the initial, the H2A change is also going to be minus 0.606. And then we do the math on 2.50 minus 0.06, and that's 2.44. So this is going to be our fourth thing that we do here, is we calculate that. Okay, we throw our numbers into our, we write our Ka expression. We still have to do the Ka expression. And then we throw in our numbers, we calculate it, and oh, lo and behold, we are done. So the math itself is actually even easier than, you know, when you have to solve for X and do a little bit of algebra. This one, you just chuck the numbers in and solve for Ka. Okay. One of the other reasons I want you to not write plus X is because sometimes what students will do is they will then write, so we're not going to write that, but they will write 2.50 minus X, and then they'll write assume X is insignificant. Question: is the amount dissociated, which is X, which is 0.060, is that insignificant compared to your 2.50? Is the amount dissociated insignificant compared to 2.50? It is quite significant. Yes, it changes it from 2.50 to 2.44. Yeah? So that's quite a lot. Sometimes it won't be really significant. Sometimes you'll do the subtraction and the dissociation amount will be quite small. And you'll be like, oh, it really was insignificant, right? Like if you say 2.50 and you're subtracting something times 10 to the negative 5, you can be like, oh, well, I don't really need to worry about that. But it requires you to make a judgment call. Yeah? So you can always just do the subtraction if you want to. All right. So don't just use X because it leads to errors. Don't assume that the change is insignificant because it often will not be. And then if we actually did that, you know, if you assumed it was insignificant, you would get 1.44 times 10 to the minus 3. And you'd get Ka as 1.4 times 10 to the minus 3. And you can see that those two values are different from one another. Yes, you don't want to do that assumption. Okay. Next example. Okay. Do you have an example too? You do, but it's filled in.
Yeah.
Yes. If yours is filled in, which most of yours will be, go get a piece of paper and cover it up. In the new version of the book that I'll have for the next set, it will be empty, but cover it up and get yourself a blank piece of paper. You guys are going to try this one, okay? Oh, and by the way, what I didn't mention is that for our unknown acid, we often use HA. Okay, because A is not an element. Yes, and A stands for acid. So if you have a weak monoprotic acid, you would call it HA. If you have a weak diprotic acid, you would call it H2A. Yeah? That's what you can call your unknown acids. There you go. So for your unknown weak acid, you could call it HA, you could call it HX, or I don't know, HW for weak, although W is tungsten. What does this dissociate into? Not this. What does that dissociate into?
The acid.
Yes.
I thought it was just something with this. It's getting associated with the
Yes. Yes.
the charges on. Do we have to worry about it?
Yes, you have to worry about the
So
charges.
H could be minus.
Yes.
Wait, H plus.
Yes.
Yes.
Yes. Yes, yes.
Right. Thing is, I don't know which one's the initial. I don't know.
Yes. What? Yeah, what are we going to do with that? We need hydrogen, but I gave you OH. What do we do?
Oh,
If you need hydrogen, but I give you OH, what do you need to do? You need to use KW.
wait, what's the point of KW?
KW is equal to, it's a K value. Do we use plus in K values?
PK.
That's what PKW is adding, but this one is, okay, you don't need to forget because it's in your data booklet.
It's equal to.
What is the KA, what is the
1.0.
KEQ for, what is the KEQ expression for this?
1.0 times connection.
No, what's the KEQ expression?
Maybe I expect.
Expression means the square brackets, and what goes in the square brackets?
Yeah, H plus OH over H2O.
Except for H2O is a liquid,
So we don't count it.
so we don't put it in there. So what is KW equal to?
H plus OH.
Yeah, H plus times. Well, how would you write the KEQ for this? KEQ is equal to
Yeah.
H plus
times OH.
times OH minus. Yes. And what is this KEQ called?
AKW.
KW. Check to see. It was one of you two, and maybe other people as well, because I haven't gotten past the first row yet. If you did not write this formula before you plugged in your numbers, you'll want to make sure you do that in the future. Okay? I can't remember which of you. Oh, both of you. Fantastic. Okay. So now you both know. Okay, make sure you've written that formula before you plug in the numbers. Yes. Oh, I'm backwards. Thank you.
Wait, how do we know which one's initial and which one's final? I forgot already.
Okay. I want you to think about it, James. There we go. Better?
Yeah. Yes.
Yay. Okay, good. Thank you.
Oh, no, not yet. Always 0. I mean, it's kind of an instinct and decrease, right? Probably. 是的。Yeah, yeah, I see. I forgot. No, now it's like this. In the newer version, so I did it in the newer version. And your page numbers are also not. They have like page 55 individual. Yeah. It's page, like, it says page 55, but it's actually page 95. So you guys are on, okay, so you have this now. And then once you do that, you will want to do, because it is a weak acid, you're going to There's no final answer for this.
There's no final answer?
They just give you the KA spectrum, but doesn't say the final answer. Which I don't know if I did right.
Well, hang on, we'll get there. Now, quick question for you. If you look at this number here and you compare it with this number here, is it insignificant?
Yeah.
Yes, so you can just say at this point that this is 0.025. No, you can just be like close enough because because to sig figs, like to many sig figs, that's what it is. Did we get 1.2 times 10 to the negative 11? Yes? Excellent. Okay, so check your work to see if you got full credit. Okay, did you write this? Did you show your plugging in? Did you get the correct number? Okay?
I would actually use 5.55.
You could use 5.55 for 5.56. I actually used 5.555555 because I just kept the number in my calculator.
Yeah.
I did not use 5.6. I used 5.55555 times 10 to the minus 7, but I didn't want to write that. Yes? But I wrote 5.6 times 10 to the minus 7 because I didn't want to write all those numbers. Because not want, write all numbers. Okay? And you can do that too. But don't change it to 5.6 times 10 to the negative 7. Don't press clear 5.6 times 10 to the minus 7. Keep the 5.5555555. If you do want to press clear, then type in 5.556 or something like that. Yes? All right, and you should get that. You get probably 1.5 marks usually for that part of the rice table. 0.5 for that. How do I know 5.6 times 10 to the negative 7 is 2 sig figs? It's not 2 sig figs, it's just what it is. Did you write your Ka expression? That's 0.5. Did you plug your stuff in? And did you get your answer to correct sig figs? There you go. Okay, I don't know what it's out of. It doesn't matter because it's not a real question, but make sure you have all those things. And did you have all your pluses and minuses? Check for them if you are missing any of your pluses and minuses on your H pluses or on your OH or on your H. If you're missing any of those, you're going to take off 0.25. Okay? And now we have some exercises. But before we do the exercises, I'm going to show you one more type of question. One more type. Because it's pretty straightforward. We are now on page 100. Well, I'm going to do it without the video, right? This is like you could study it on your own. Question. Question. Would you rather do the practice exercises right now from the previous one and watch this at home on your own and fill it out? Because you can watch it. Or would you rather I go through this with you right now? You want me to go through it right now? Okay, we're going to do that then. So don't talk. Okay, thank you. All right, so we have 500 milliliters of oxalic acid, and it has a pH of 1.095. How many moles of H2C2O4 were initially added to the sample? Whew. So this one's a little tricky. If we want the moles that are in the sample, really what we want is the moles in 500 milliliters. In order to find the moles in 500 milliliters, what we really want is the moles per liter. What do we need the moles per liter of? We want the moles per liter of H2C2O4. And moles per liter of H2C2O4 is called the what of H2C2O4? It's called the molarity of H2C2O4. So what we don't know is we do not know the concentration of H2C2O4 equals we don't know what. Yes? And if we don't know that, we can say, let's let that be X, shall we? X is a good unknown. Is this the initial or the equilibrium concentration of H2C2O4? Initial. Always initial. Anytime you are asked for or are given a concentration of the acid, it will be the initial concentration of the acid. Okay? Before we were given it, now we're being asked for it. What other information are we given? We're given pH. pH is equal to 1.095. Is that useful to us for solving these kind of questions? We should transfer it to H. So we're going to say, okay, our concentration of hydrogen is equal to 10 to the negative pH, which is 10 to the negative 1.095, which is 12.4451. Okay. Why do I have so many digits?
If you don't want, because if you round it off, it will be wrong.
Yeah, if I round it off, it'll be wrong. And remember, in a pH. Oh, actually, I'm so sorry. What is wrong with me? Ugh. 1.095. I think I didn't make it negative. Ah, that's the wrong number. 0.08035. That's better. Molar. I forgot to make it negative before I.
And it became basic.
Yeah, exactly. So, well, no, it did not become basic because hydrogen ion concentration would have been like 12 molar.
Oh, yeah.
Yeah, which is like way too big. Okay. H2C2O4, what type of acid is this? Strong or weak? Weak. So what tools do we need to use? Rice and Ka. So let's start ourselves now that we have our hydrogen ion concentration and we know that our X is our acid concentration. Let's start with our Rice table. H2C2O4 in equilibrium with H plus HC2O4 minus, that's our R. And you'll notice, how many hydrogens did I take off? Just one, because only the first one is important when it's on its own. Okay, ICE. This is our initial concentration, is X, so we're going to put our X here. What are the initial concentrations of hydrogen and the other guy? 0, because they're always 0. What should we fill in next? yeah, we're going to have pluses and minuses, so we can put in a plus and a plus and a minus. We know that hydrogen is 0.08035. So where would we put that? Yeah, that is our equilibrium concentration, 0.08035. And that lets us say that our change in hydrogen is plus 0.08035. And if that change is 0.08035, then all the other changes are also 0.08035, 0.08035. Whew.
We're just doing like a 500 millimeters.
Later. What next? Ka. Expression. H plus HC2O4 minus over H2C2O4. What next? Well, let's start by plugging in the things that we do have. We do have these guys, right? 0.08035 squared divided by x minus 0.08035. Oh no, now I have Ka and I've got an x. What on earth do I do? I can't have two unknowns. No, the x can't be insignificant because that is our initial concentration of our acid.
You look at the solubility. No, this one.
Do we look at our pink sheet? What would we find on our pink sheet? We would find Ka on our pink sheet. Go find it. Five 5.9 times 10 to the negative 2. All right. Now I'm going to show you just for a moment when I'm doing the algebra here what I used to do when I was in high school and why it is extremely inefficient and how to do it better. Okay, so don't write down what I'm going to write down. Okay, what I would do is I'd be like 5.9 times 10 to the minus 2 times x minus 0.08035 equals 0.08035 squared, and then I'd have 5.9 times 10 to the minus 2x minus blah 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 equals blah 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 blah, and then I would like there was a lot of work involved. Yes, but what I could do instead of multiplying this all out, 5.9 times 10 to the negative 2 times 0.08035 equals, and I get 4.74 times 10 to the minus 3. This seems horrible, yes? Lots of numbers all over the place. You can get by with a lot less numbers by yes, you bring this guy up. This guy comes up here. And this guy moves down here. Yes? Yes? That's how algebra works? Yes? Not that it won't work the other way, but anyway, so I bring this up and I say, okay, x minus 0.08035 equals, and this is still up here, 0.8, whoops, 0.8035 squared over, and now this guy comes down here, 5.9 times 10 to the minus 2. And now life is a lot better because now we can say x minus 0.08035 equals 0.08035 squared divided by 5.9 negative 2 equals 0.1094. X is equal to 0.1094 plus 0.08035, which is 0.189776. However, how many sig figs should I have in this number?
You look to the very beginning.
I look to the very beginning and I also look at the Ka value that I used.
Oh, 2.
So yeah, 2 is the smallest number. I had more than that in my other numbers, but my Ka value had only 2 sig figs. So this then has to round to 0.19. And am I done? Box it, done? No, what do I have to do? What was I looking for? That is molar. And that is what? That is the concentration of let's go look. We solved for x. What is x? It is the concentration of H2C2O4. Yes? And that, my friends, is our final answer. Unless I've done something wrong. Did anybody get anything different from me? No? Okay. Sometimes when I do things, I, punch buttons wrong, forget a 0, forget a negative. And that's how you do that type of question, okay? So for homework, you guys are going to do 4.3c. Exercises. Yes. Oh, it wasn't asking us for molarity, was it? It wasn't. Look at me not reading the question. Good for you. Oh, Bella, clever girl. Nice. We didn't want molarity. We wanted moles. Oh dear. Okay, so we're not done. Let's get rid of that box. How do we find the moles if we know that this is the, in fact, never mind. That is our moles per liter, right? And we know that we have 500 milliliters. How do we find the moles? If we know the moles per liter and we know the milliliters. This is just unit cancellation. This here is 0.5000 liters. Yes? How do I find moles? I need to cancel the liters and find the moles. And I should actually use my unrounded number. So 0.1897 or 8, I guess, times 0.5 equals 0.0949, which then becomes 0.095 moles of H2C2O4. Is good? Okay. So, homework please. What do we got there? 4.3. Yes.
Would it be forcing things to put your point five?
Good question. How did we get there though? Way back there, way back there, we had 2 sig figs. So this actually has 2 sig figs. That number there, even though I've written more digits, has 2 sig figs. So yeah, you got to go back and you got to like go, what's in my question? Did I use a Ka from the table? Right? Anytime you use a Ka from the table, you are limited to 2 sig figs. Okay, that was a good question though, because you are not the only person thinking that. All right. All right.
I mean, there is only one choice of question. Oh, this is example 2 students. There's 1, 2, and oh my god, there's only 2 of them.
Page 99. You can do numbers 1 through 4. And then page 102. One oh three. So that's 6 questions altogether. I know that sounds like a lot, but there's only 2 questions on page 102, 103. There you go. And I think tomorrow we finish the unit. Quiz Monday on Ka, that's section 4.3. Let me get rid of my Science 9 test because I will write that somewhere else. And then your test would be Friday. Unit 4 test. Friday. You want to do it Wednesday? Friday's good? Okay. April
17.
Thank you. By the way, your test won't get marked over the weekend because my report cards are due on Monday. But then you don't have to worry about it over the weekend. Yes? And tomorrow I will have your review. for you that you can take home over the weekend and start working on? Huh? No. Those things are not tomorrow. Working very hard. I gotta stick that in my book so I don't forget. There we go.